Cold Working of Materials, Project Number 3, by Owen Champion, Patrick Nimina, and Josh Webb. Steel Dagger Cold Working Goals and Plans. The goal of the assignment is to cold work a steel rod into a circular dagger with the dimensions of 3 centimeters in diameter, greater than 800 megapascals of tensile strength, and greater than 15% ductility. A single cold working treatment to the steel rod won't get the constraints of ductility greater than 15% and a tensile strength greater than 800 megapascals. This is because the ductility won't hold above 15%. To get these numbers, we must take multiple passes with cold working and annealing. This will allow the metal to heal and be cold worked again.
Cold working graphs for steel. Alright, now as we see the graphs below, what these graphs do is these graphs allow us to see how cold working will affect the properties of the steel. Now, the cold working done on steel is very important because if we look at it, too much cold working done at one time will achieve the dimensional and tensile strength goals, but it also falls short of the elongation goal. And if you look on the flip side of it, if you don't have enough cold working, you'll fall short of the dimensional properties, but you'll get the elongation and the tensile strength. So too much of it, you can miss out on the elongation goal. Too little of it, you can miss out on the dimensional properties, which is why annealing is so important, because with annealing, we're able to rest the cold working while also keeping the dimensions that were achieved. So the graphs down below, as it's labeled in the corner, ductility of cold work steel is in the blue, so which is this line right here, and tensile strength of cold worked in steel is also in blue, which is this line up here. All right, now we're going to look at how we achieve the desired strength and ductility. Now, on the last slide, we said that too much cold work can fall short of the elongation goal, and too little cold work can fall short of the dimensional goal. So for our strength and ductility, in order to achieve the desired strength and ductility, multiple cold work passes are required. Now, if we look up here, we see our formula, which is 1 minus the final dimension over the original dimension squared times 100. So for our first cold work, we're going to do 1 minus 3.2 over 5 squared times 100, which gives us 59.4%. I'm going to write it down here. 0.04, sorry, percent. All right. Now, the final percent cold work that is required to get the correct ductility and tensile strength is around 12. Now, we're going to do that down here with the second cold work, which is 1 minus 3, which is our final, over 3.2 squared times 100, which equals 12%. All right, now on the first cold working, the diameter targeted should be less than the final target, which will allow you to have multiple cold works, which gives you the final strength and ductility. Alright, now let's analyze the cold working graphs for steel at 12% cold work. So if we look at the graph to the left, ductility of cold work steel is in blue. Now the blue line that is shown on the graph is where the original cold working would leave the steel. So this blue line right here. And that's after the annealing process. And when the second cold working is done, we're going to look to the right hand graph and look at this red line right here. When the second cold working is done, the red line shows where the steel sits in terms of hardness and ductility, which is our red line right here. And the ductility of the cold work steel is still in blue, which I don't know if you can see it, but it's this one right here. Just pointing an arrow at it. And the tensile strength of cold worked steel is also in blue, which is right up here. That's the arrow.
Now we're going to use the same process that we used on the steel dagger onto the aluminum dagger. For the steel dagger, we use the equation percent of cold work equals 1 minus the final diameter over the original diameter squared, and then multiplied by 100 to get the percentage. And for the steel, to fit the constraints of the steel, we needed greater than 15% ductility and greater than 800 megapascals. In order for us to do this, we split it into multiple cold works, and our first cold work was 59.04%, and our second cold work was 12.1094%, which allowed us to get in between those constraints. Now for the aluminum dagger, we're going to use the same process, and we're going to use the graphs to find how the steel reacts compared to the aluminum. Now using this cold working graph for the 3105 aluminum, we drew a line through at the 12% mark, which is what we used in the previous cold working, which is after the annealing process, which was after the 59% cold work at the beginning. But the annealing process after the cold work reset it back to the original tensile strength and ductility, but just changed the diameter to 3.2 centimeters. Now cold working from 3.2 centimeters to the 3 centimeters, it takes only 12% cold working, which gave us roughly a 9% ductility. From looking at the graph, it was roughly 9%, and it came out to be 20 KSI, and converted to MPa, it was roughly 138 megapascals. If we were going to compare this to the steel constraints, it wouldn't fit it even close. The ductility was well below 15%, and the tensile strength was greatly under the 800 megapascal mark. This is good for our understanding because now we can see that the different materials change the way that our cold working process affects the strengths of the materials that we're using. Cold work hardening. Through our results and our calculations, we learned that both materials can be subjected to the same cold working, but they can have drastically different properties at the end of their cold working cycles. For instance, for steel, the cold working introduced high dislocation density, and the dislocations interacted and entangled, which impeded the motion, which raised the strength. Within this, we had microscopic slips and like the atoms sliding, and elongated grains, and which increased hardness. And comparing the aluminum to the steel, it had similar dislocation strengthening, but aluminum has a higher stacking fault energy, which makes the dislocations more easily rearranged. So it promotes like a dynamic recovery, which makes it harder for it to
get harder. So this results in a less dramatic hardening than steel, because steel jumped from around 700 megapascals to almost 900, and then the aluminum went from like 15 ksi to 30, which was 15 ksi is roughly 100 megapascals, so it's a lot less dramatic. So microscopic signs for the aluminum would be less pronounced slips and slides, and more quick grains, unless heavily deformed. And the cold working is able to make the materials stronger because the movement of material allows molecules to slide, making the networks, which can in turn make this material stronger, but more brittle because the elongation also decreases. The annealing process is able to dissolve these networks, which reverts the material to its properties that it had before the cold working. So the ductility went back to the original ductility, and the tensile strength went back to the original tensile strength. And this allowed the diameter to stay the same, so it just reset the strength of the material.